Hey, this is Mr. Janes. In this video, we'll be talking about intersecting lines and systems of equations. Suppose you have a graph with two lines on it, and you need to figure out where those two lines intersect. Or, on the other hand, suppose you have two equations, and you need to figure out what values of x and y are solutions to both equations at the same time. Turns out that those two problems, both two intersecting lines on a graph, and when the solutions to two equations are equal, end up being the same exact problem. I'll show you how that works in this video, first graphically, second algebraically. So this is systems of equations. To start, we will graph the following pairs of lines and find their point of intersection. Then, once we're done, we'll verify or check our solution by substituting in the coordinates of our answer. I'll do the first one, and then I'll ask you to pause and try the second one. Let's get started. I'll graph the first line here using blue. So we've got y equals 2x minus 1. It's got a y-intercept of negative 1, so I'll start there. And a slope of 2, which we could also interpret as 2 over 1. So we can go up 2 and over 1 to get to our next lattice point, right? Then we can also go backwards if we wanted to. And then the second equation here, I'll use red for. Y equals negative 1/2 x plus 4. Again, it's got that y-intercept of 4, so we'll start by putting a point there. And it's got a slope of negative 1/2, which means we'll have to go down 1 and to the right 2. I'll continue that, and I can even go in the other direction. Okay, and now I'll draw my lines. Make sure that you're using a straight edge or a ruler to draw those lines. Make sure you have arrows on the ends of them. And now we're looking for the point where they intersect. Now that seems to be this coordinate right there. So the point of intersection, or the solution to these two equations, seems to be when x is, let's see, 2. X is 2, and when y is 3, better known as the point 2, 3 in parentheses. So it looks like we found the point of intersection of these two lines at 2, 3, but what else does this point mean other than just where these two lines cross? Well, it turns out that the coordinate 2, 3, or 2 for x and 3 for y, is also a solution to both of these equations at the same time. In other words, we could take the numbers 2 for x and 3 for y and substitute those into the first equation or into the second equation. And in both cases, we will get both sides of the equal sign to have the same number. They are solutions to both the first and the second equation. Let's check to make sure that that's actually true by doing a little bit of algebra. So what I'm saying is that you could take the first equation, y equals 2x minus 1, and the second equation, which is y equals negative 1/2 x plus 4, and you could substitute in 2 for x and 3 for y. Let's go ahead and do that. So this becomes, instead of y, now I have 3, because again, y equals 3 at the point of intersection, equals 2 times 2, again 2 for x, minus 1. And the second equation becomes 3 equals negative 1/2 times 2 plus 4. Now let's go ahead and simplify these equations a little bit. So the first one, we've got 3 stays on that left-hand side. Then we've got 2 times 2, which is 4, bringing down that minus 1. And then 3 again on the left-hand side. But then 4 minus 1 is 3. 3 equals 3. Wow. That means that the solution 2, 3 is a solution to the first equation. What about the second equation? Well, again, the 3 comes down to that left-hand side. We've got negative 1/2 times 2. Remember how to multiply fractions. We can take that whole number and give it a denominator of 1. And we multiply the numerator and denominator separately. So negative 1 times 2 is negative 2. 2 times 1 in the denominator is 2. Bring down that plus 4. I'm going to move up here for this next part. So then we've got 3 equals, well, negative 2 over 2. That's just negative 1. So 3 equals negative 1 plus 4. Bring that down. And then negative 1 plus 4, that leaves me with 3. So again, 3 equals 3. That means that the point 2, 3 is also a solution to the second equation. So we've shown that the point of intersection of two lines, in this case 2, 3, is also the values for x and for y that are a solution to both of these two equations at the same time. That's pretty interesting. At this point, I'd like you to go ahead and try the second problem right here. Go ahead and graph these two lines, y equals 2x plus 2 and y equals 3x plus 4 on the same grid right here. Find the point of intersection, which will be your solution to these two equations. When you do, go back, just like I did, and check your work. Take that solution and substitute it in for x and y in both the first and the second equation. Once you're done, unpause the video to make sure you've done it correctly. The answers will come up on the screen in 3, 2, make sure you try this first, and when you do, I'm going to do the first one in blue and the second one in red. Alright, here are the answers in 3, 2, 1. And here are two lines graphed. Make sure that as you're looking at this, you are not just copying down answers, but trying to understand it. Whether you got it right or wrong, seeing your mistakes and trying to learn this a little better. So again, our first blue line, starting at y-intercept of 2, and then with the slope of 2, so over 1 up 2, and in the other direction as well. The red line we've got here with a y-intercept of 4 and a slope of 3, so again, we could have gone up 3 and over 1, or we could also go back down the other way, keeping that positive slope. Either way, it looks like our solution here is -2 for x and -2 for y. So the point -2, comma -2. Well, just to be sure that that is our solution, let's check it out here. Okay. Let's take our solution, -2, -2, and substitute it in for x and for y, just like we did in this first example over here, to ensure that that point of intersection is also a solution to both of these equations. Go ahead and try that now. The answers will be up in 3, 2, make sure you've tried it. Here are the solutions. And here is the check. Looks like for both the first and the second equation, the solution -2 for x and -2 for y checks out. But what if we didn't have a graph in front of us? Could we somehow find the point of intersection algebraically? Well, the answer is we can. In these first two examples, we learned that the point of intersection, right here in the first example, is where the y values and the x values for both the red line and the blue line are the same. That means that at the point of intersection, this y value and this y value will in fact be equal to each other. In other words, this 2x minus 1 is equal to this y, which is equal to this y, which is equal to -1/2 x plus 4. In fact, they'll all be equal. I could just simply take this 2x minus 1 and substitute it in for this y and set it equal to this other equation. Let's see how that actually works in the next two examples. Using substitution, an algebraic method. The point of intersection is where the solutions, the x and the y values, of both equations are the same. We learned that in the last two examples. Now, if we assume that the values are equal for both x and y, we can use a method called substitution to find the point of intersection algebraically. Again, where those two lines intersect on a graph, okay, they will have the same y value and the same x value. So these two y values in both the first equation, y equals 2x minus 1, and the second equation, y equals -1/2 x plus 4, will be the same. Thus, we can literally take this 2x minus 1, since it's equal to y, which is equal to this y, and set it equal to -1/2 x plus 4. Let's do that right here. 2x minus 1 equals -1/2 x plus 4. All that's left to do now is solve. We have -1/2 x on the right hand side, so I'm going to add 1/2 x to both sides to try and get those all the x's on the left hand side. In case you've forgotten how to add fractions, and we've got 2x plus 1/2 x, so 2 plus 1/2. We need to have common denominators, so 2 is the same as 2 over 1. I could multiply both the top and the bottom of that fraction by 2 to get 4 over 2 plus 1/2. Now they've got common denominators, both are 2, so I can add the numerators. This is 5 over 2, or 5/2. So I'm left with 5/2, or 5 over 2x. Bringing down that -1 equals 4. I can now add 1 to both sides, and we're left with 5/2 x equals 5. Now, to isolate the x by itself, I've got 5 over 2x. I'm going to multiply both sides by 2 over 5. So this side by 2 over 5. Now, what that does is when I multiply fractions, in case you've forgotten, you multiply the numerators and the denominator separately. So over on the left-hand side, I have 2 times 5, which is 10, and 5 times 2, which is 10. And 10 over 10 is just 1, so I'm left with just x. On the right-hand side, though, I've got 5 times 2 over 5. I can put the 5 over 1. And so now multiplying, I've got 5 times 2 in the numerator, which is 10. And then in the denominator, I've got 1 times 5, which is 5. And 10 over 5 is the same as 2 over 1, or just 2. So in this case, x equals 2. Now, okay, well, x equals 2, but don't I need both an x value and a y value as a solution to both of these? The answer is I do. So how can I figure out what the y value is? Well, all I need to do is take 2 and substitute in for x in either the first equation or the second equation and solve for y. Now, the first equation looks a little easier, so I'll start with that. So if I have y equals 2x minus 1, and I just learned that x is 2, I can write y equals 2 times 2 minus 1. 2 times 2 is 4. 4 minus 1 is 3. So y must be 3. Of course, if you wanted to, you could have substituted 2 into the other equation, and we should hopefully get the same answer. Let's check it out. The second equation was y equals negative 1/2 x plus 4. Substituting in 2 for x gives me y equals negative 1/2 times 2 plus 4. In the problem above, we learned that negative 1/2 times 2 is the same as negative 1 plus 4. And so y equals 3. So either way, I get y equals 3. So the solution to this is going to be 2 for x and 3 for y. That's my final solution. Remarkably, that's the same exact solution I got graphically, 2, 3. Now, if solving the equations was a little difficult for you this time because of all the fractions, don't worry, we'll work with fractions more in class. What I need you to understand right now is the process. Remember, we started by substituting in 2x minus 1 for y in this equation to end up with this equation. We solved to find out what x was. Then we substituted back in to either equation, or both if you want to check yourself, to find out what y was, and ended up with our final solution. At this point, I'd like you to pause the video and try and solve this system of equations right here by substitution, algebraically, just like we did in this example, to the left. And I promise you this time, there won't be any fractions. Whew! We'll work on those more when we get to class. So, pause the video here. The answers will be up in 3, 2, make sure you're trying this. Here they are. First, here's the setup in purple, just the same as I did the setup on the left-hand problem. And now we're solving for x. Turns out that x is negative 2. Then we're taking either of our two equations, or both of them if you want. Now that we know that x is negative 2, we can substitute in negative 2 for x to find out what y is. So, like that. Or y equals 3 times, now x is negative 2, plus 4. And we can simplify those. And in both instances, we get y equals negative 2, which means that our final solution is going to be negative 2 for x and negative 2 for y. Now that's the point of intersection of both of these, and we've done that using algebra, the substitution method. But turns out it's the same solution as I got above when I was looking at the graph. So in this video, we've learned how to find the intersection of two lines in two different ways. First, by graphing, finding the point of intersection, and also checking our work. And second, by using substitution to substitute one equation into the y value of another, set up that equation, solve for one variable, and then substitute back in to find the value of the other variable. Lastly, don't worry about the last two questions in this video.